Hello everyone, I hope you are doing well. My name is Aunur Rahman and I'm going to present my paper to you. And the title of the paper is Cross-Modal Knowledge Distillation from Wearable Physiology to Wi-Fi CSI for Sensorless Agitation Detection. From the picture, we can see that Alzheimer's disease and related dementia problems are increasing very fast, and many more older people will need care in the future. Millions of Americans are aged 65 and older already lived with these diseases, and this number will grow a lot by 2050. At the same time, the number of caregivers is not growing as fast. Many caregivers are unpaid, and the picture shows that the need for caregivers will almost double. This means each caregiver will have more work and more pressure. From the picture, we can see that agitation is one of the major problems for ADHD patients. Agitation means the patient may become angry, confused, restless, or upset. They may walk around too much, shout, cry, or refuse help. This makes daily care very hard. A caregiver may not know how to calm the person, and this causes more stress and more fear. Agitation can also lead to falls, injuries, or the patient leaving home and getting lost. These situations are dangerous, especially for older people. We can also see that patients lose personal independence as the disease becomes worse. When patients cannot take care of themselves, caregivers must do more. If the patient is also agitated, the work becomes even more difficult. Caregivers can feel tired, worried, and emotionally hurt. Over time, this can affect their personal health and personal sleep cycles. Because of all these problems, the image actually suggests us that remote monitoring is important. With monitoring systems, agitation can be noticed early. Caregivers or doctors can get alerts and help the patients before the problem becomes very serious. And this can prevent accidents, lower stress, and make life safer for both the patients and caregivers. So that's why we are focusing on predicting the agitation episodes. And we are using Wi-Fi CSI for this because we want to ensure the privacy and user comfort. Because when people wear wearable devices, they don't feel that much comfort. And if we use camera or other visionary devices, it will breach their privacy, and every people is concerned with privacy, so that's why we are using Wi-Fi CSI for monitoring ADHD patients so that we can ensure safety along with the privacy. So for our model we are using two different data set. The first one is vegetation and the second one is the physiological data. The vegetation data set is a contact free vegetation recognition data set with physical activity, and the data set is from 18 older adults who simulate the activities. And there are 9 classes, and those are normal walking, sitting normally, sit to stand, tapping, rubbing the table, wringing hands, disturbed walk, flipping objects, and kicking. We can also classify these 9 classes into 3 stages. Like the first one is the normal state where people walk normally and they sit normally. And then we can say the next stage is mild agitation where people flips where people flip the objects and ring and show ring hands activities, or they can rub the table. But in the acute agitation stage, people actually sometimes kick some objects and they show disturb walking. So yeah, we can classify those activities into three classes so that caregivers can more easily interrupt. And then the physical data is collected using a empirical 4 watch, where there are basically two classes like normal agitation and the normal state, and that set is collected from actual patients in a nursing home, and 20 patients were participated in this experiment. So here basically you can see our knowledge distillation framework, and it has two phases. One is the training phase and second is the deployment phase. In the training phase, we are using both wearable dataset and Wi-Fi CSI dataset. But in the deployment phase, we will only use the CSI dataset because the mapping is already completed in the training phase. So our architecture do not need any wearable dataset in the deployment stage. So basically, we can actually monitor patients using our Wi-Fi CSI data, and it also captures the physiological relationships with the subcarriers from our knowledge distribution framework. So first we need to collect the wearable physical data in the training phase, and then we need some pre-processing because we want to extract the outliers and we want to remove the noises from the wearable dataset for further processing. Here you can see we have already extracted 7 features from the dataset, and these are kurtosis, mean, standard deviation, minimum, maximum skewness, and energy mean. We need to calculate the mean because when people are agitated, their mean is remains higher than their typical calm level. And in the kurtosis, high kurtosis means the signal has many rapid spikes instead of smooth changes, which helps us spot the agitation. And we also use the standard deviation for same reasons because when people are agitated, they actually show some repeated activity, and the signal also indicate that this contains repeated activity spikes and it is an early sign of agitation. We also need to calculate the minimum and maximum because it indicates the pauses and relaxations, so we can actually get the early sign of agitation. We are also using the skewness and energy mean for this because a positive skew indicates repeated sudden spikes in signaling the agitation states. And the energy mean is also important because in intense motions or powerful physiological reactions, the magnitude is very high. After extracting those features, we need some pre-processing steps where we actually removed the noises and also removed some outliers to train our dataset into the random forest teacher model. Here you can see our random forest teacher model architecture. And for this, we need to extract our dataset and we need some preprocessing. And for that, we have used the spike and butterworth algorithm. And then we split our dataset into 60-second frames and we again extracted 7 features from it. And then we used 2 algorithms for handling the imbalanced dataset because our dataset is highly imbalanced, so it is always show biasness towards the calm state, and that's why we have used random undersampling and adaptive synthetic sampling for handling the imbalanceness. Then we have used the Optune algorithm for hyperparameter tuning, and then finally we have trained our model, the random forest model, based on our preprocessed dataset. And we also evaluated our dataset, evaluated our model based on the performance. For training our teacher model, we calculated the teacher embedding, teacher logics, and domain loss. Teacher embedding is needed because it transfers deep knowledge from the teacher model to the student model. The teacher model is trained using our wearable dataset, which provides strong and reliable information about agitation. The teacher embedding represents high-level behavior patterns learned from this rich data. By forcing the student model to match these embeddings, the student does not only copy the final answer but also learns how to represent agitations internally, which actually mapped our physiological data into the Wi-Fi CSI data. And this makes the student model smarter and more stable when it works with Wi-Fi CSI dataset. We calculated the teacher logics because they guide the student model using soft predictions instead of only correct or incorrect labels. The teacher logics show how confident the teacher is about agitation levels. This extra information helps the student understand difficult cases better. For example, the student learns whether a case is slightly agitated or very agitated instead of just yes or no. This makes training smoother and improves accuracy, especially when the data is too noisy. We, we have also calculated the domain loss, and it is needed because the teacher and student use different types of data. The teacher uses wearable sensor data, and the student uses Wi-Fi CSI data. These are two different domains. Domain loss forces the student embedding to look similar to the teacher embedding even though the data source is different. This helps the student learn features that are independent of the data type and focus on behavior patterns instead. Without domain loss, the student may fail when working on Wi-Fi CSI data alone. So, together teacher embedding teaches how to think, teacher logics teach how confident to be, and domain loss teaches how to handle different data sources. This makes the student model reliable while keeping it lightweight for real-time use. Now, after completing the teacher models training and calculating the teacher embedding, teacher logics, and domain laws, we are now give our focus on Wi-Fi CSI dataset, and we actually use the phase and amplitude of the CSI subcarriers. After some pre-processing, we need to reduce the dimensionality of the CSI dataset because there are 270 subcarriers for each channel, and we are using phase and amplitude, and so it will actually increase the computational cost. Here you can see our CSI net model architecture, and we have used CSNet model architecture to reduce the subcarriers. The result is a 74 reduction in input width and a tensor of shape 2 by 3 by 80 instead of 2 by 3 by 270. We have calculated the phase and amplitude variance. We have also calculated saliency, and we have then calculated PCA and also calculated the ANOVA score to extract the subcarriers, and thereby we have selected 80 subcarriers from 270, which is very much efficient. Here you can see in the picture that the first 50 subcarriers actually carry the necessary informations. You can see the spikes, the rest of the signal is steady. So that's why we just took the first 80 subcarriers, which actually contains most of the necessary informations. For that, we have used the mobile net lightweight architecture as a student model to train the Wi-Fi CSI dataset to classify 9 different activities. Then we combined our student model with student embedding, soft knowledge distribution loss, and domain classifier. Student embedding is helpful because it is the feature space where the student model learns to represent important patterns for classification. Instead of only producing a final label, the student embedding captures hidden information about behavior, movement, and activity related to agitation. A well-learned embedding makes classes easier to separate. When the embedding is good, the classifier can clearly tell the difference between agitated and non-agitated. Matching the student embedding with the teacher embedding also helps the student to learn meaningful features even when the Wi-Fi dataset is noisy or limited. And then we have used soft knowledge distillation loss, and it is helpful because it trains the student model using more information than just correct or incorrect levels. Instead of learning only right or wrong, the student learns from how confident the teacher is about every class. These soft probabilities show which classes are similar and which are very different. This makes learning smoother and helps the student avoid overfitting. It also improves accuracy when class boundaries are unclear. Our soft knowledge decision loss helps the student model learn better decision rules and generalize well to new data. So together, the student embedding actually improves our model to learn new features, and the soft knowledge decision laws improves how the decisions are made. And these two combinedly make the model more stronger and more reliable to classify the 9 different activities. Here you can see the result. Our teacher model outperformed the others state of the art models. Here you can see the comparisons. So our proposed methodology gives almost 96.9% accuracy with a 77% balanced accuracy. And the AUC is also really high, and it is nearly 0.94. You can also see that our model actually used 42 features, and it also outperformed the regular random forest classifier. Here you can see the confusion matrix for our classifier, and you can see that our model performs pretty well in detecting agitation and non-agitation classes. Here is the result for student model. From the confusion matrix, you can see that our model can perform very well in classifying different activities. So the model actually classified 9 different activities. The model performed very well in detecting the calm, disturbed walking, flipping objects, kicking, rubbing tables, sitting or standing activities. Basically, these activities involves high movements, so the model can classify them very easily. Our model suffers in classifying tapping and ringing hand activities. These activities involves tiny movements, and sometimes our CSI does not reflect those activities very clearly. And these activities, the tapping and wringing hands, are also related with mild agitation. So, and then the flipping objects, kicking, and rubbing table is related to high agitation. And since our model can very accurately classify the high agitated states, the caregivers can easily take necessary steps to intervene the agitated people from doing something bad. Here you can also see the training losses for our student model. In the future, we will apply our framework in a real facility care, and we will receive the feedback from the caregivers and the doctors, also from the patients. And we are planning to work on person specific calibration. We will investigate personalized modeling to comprehend how distinct physiological characteristics such as skin conductance or heart rate variability uniquely impact the CSI signal distortions. And finally, thank you. Thank you so much for attending the conference, and thank you for listening the presentation.